Chapter 5. Initial Value Problems for Ordinary Differential Equations. Introduction. The motion of a swinging pendulum under certain simplifying assumptions is described by the second-order differential equation d squared theta dt squared plus g over L sine theta equals 0, where L is the length of the pendulum, g equals 32.17 feet per second squared is the gravitational constant of the Earth, and theta is the angle the pendulum makes with the vertical. If, in addition, we specify the position of the pendulum when the motion begins, theta of t naught equals theta naught, and its velocity at that point, theta star of t naught equals theta naught star, we have what is called an initial value problem. For small values of theta, the approximation theta approximately sine theta can be used to simplify this problem to the linear initial value problem d squared theta over dt squared plus g over L theta equals 0. Theta of t naught equals theta naught, theta star of t naught equals theta naught star. This problem can be solved by a standard differential equation technique. For larger values of theta, the assumption that theta approximately sine theta is not reasonable, so approximation methods must be used. A problem of this type is considered in Exercise 8 of Section 5.9. Any textbook on ordinary differential equations details a number of methods for explicitly finding solutions to first-order initial value problems. In practice, however, few of the problems originating from the study of physical phenomena can be solved exactly. The first part of this chapter is concerned with approximating the solution y of t to a problem of the form dy dt equals f of t comma y for a less than or equal to t less than or equal to b, subject to an initial condition y of a equals alpha. Later in the chapter, we deal with the extension of these methods to a system of first-order differential equations in the form dy1 dt equals f1 of t comma y1 comma y2 up to yn, dy2 dt equals f2 of t comma y1 comma y2 up to yn, dyn dt equals fn of t comma y1 comma y2 up to yn for a less than or equal to t less than or equal to b, subject to the initial conditions y1 of a equals alpha 1, y2 of a equals alpha 2, yn of a equals alpha n. We also examine the relationship of a system of this type to the nth order initial value problem of the form y of n equals f of t comma y star comma y double star y to the n minus 1 for a less than or equal to t less than or equal to b, subject to the initial conditions y of a equals alpha 1, y star of a equals alpha 2, y to the n minus 1 of a equals alpha to the n minus 1. Differential equations are used to model problems in science and engineering that involve the change of some variable with respect to another. Most of these problems require the solution of an initial value problem, that is, the solution to a differential equation that satisfies a given initial condition. In common real-life situations, the differential equation that models the problem is too complicated to solve exactly, and one of two approaches is taken to approximate the solution. The first approach is to modify the problem by simplifying the differential equation to one that can be solved exactly, and then use the solution of the simplified equation to approximate the solution to the original problem. The other approach, which we will examine in this chapter, uses methods for approximating the solution of the original problem. This is the approach that is most commonly taken because the approximation methods give more accurate results and realistic error information. The methods that we consider in this chapter do not produce a continuous approximation to the solution of the initial value problem. Rather, approximations are found at certain specified and often equally spaced points. Some method of interpolation, commonly Hermite, is used if intermediate values are needed. We need some definitions and results from the theory of ordinary differential equations before considering methods for approximating the solutions to initial value problems. Definition 5.1. A function f of t, y is said to satisfy a Lipschitz condition in the variable y on a set D subset of R squared if a constant L greater than 0 exists with the absolute value of f of t, y1 minus f of t, y2 is less than or equal to L times the absolute value of y1 minus y2, whenever t, y1 and t, y2 are in D. The constant L is called a Lipschitz constant for f. Example 1. Show that f of t, y equals t times the absolute value of y satisfies a Lipschitz condition on the interval d equals t, y such that 1 is less than or equal to t less than or equal to 2 and -3 is less than or equal to y less than or equal to 4. Solution. For each pair of points t, y1 and t, y2 in D, we have the absolute value of f of t, y1 minus f of t, y2 equals the absolute value of t times the absolute value of y1 minus t times the absolute value of y2 equals the absolute value of t times the absolute value of y1 minus the absolute value of y2, which is less than or equal to 2 times the absolute value of y1 minus y2. Thus, f satisfies a Lipschitz condition on D in the variable y with Lipschitz constant 2. The smallest value possible for the Lipschitz constant for this problem is L equals 2, because, for example, the absolute value of f of 2, 1 minus f of 2, 0 equals the absolute value of 2 minus 0, which is equal to 2 times the absolute value of 1 minus 0, which is equal to 2. Definition 5.2. A set D subset of R squared is said to be convex if whenever t1, y1 and t2, y2 belong to D, then t1 minus lambda t2, t1 minus lambda y2 also belongs to D for every lambda in 0, 1. In geometric terms, definition 5.2 states that a set is convex provided that whenever 2 points belong to the set, the entire straight-line segment between the points also belongs to the set, as seen in figure 5.1. The sets we consider in this chapter are generally of the form D equals t, y, such that A is less than or equal to t less than or equal to b, and negative infinity is less than y less than infinity for some constants a and b. It is easy to verify, see exercise 7, that these sets are convex. Theorem 5.3. Suppose f of t, y is defined on a convex set D subset of R squared if a constant L greater than 0 exists with partial f over partial y of t, y is less than or equal to L for all t, y in D, 5.1, then f satisfies a Lipschitz condition on D in the variable y with Lipschitz constant L. The proof of Theorem 5.3 is discussed in Exercise 6. It is similar to the proof of the corresponding result for functions of one variable discussed in Exercise 27 of Section 1.1. As the next theorem will show, it is often of significant interest to determine whether the function involved in an initial value problem satisfies a Lipschitz condition in its second variable.